Welcome to the deep dive. Today we are taking our sources and really extracting the core insights from the HashiCorp Terraform Associate 003 exam material.
Yeah, the 003 exam is a big one.
It is. And our mission today is to specifically explore how Terraform integrates with CI/CD pipelines. So things like GitLab and GitHub Actions and, why that integration is completely transforming how modern infrastructure is built.
Right. It's a total game changer for how teams operate.
Exactly. But to really understand why this material is so critical, I want you to imagine a scenario for a second. So you wake up, you grab your morning coffee, you sit down at your desk, and you open up your team's cloud dashboard.
Oh, boy. I know where this is going.
Right. Suddenly, your heart drops into your stomach. Your entire production infrastructure has been altered overnight. Like, servers have been moved around, databases have been completely reconfigured, and your firewalls are suddenly routing traffic into just a void.
Yeah, absolute panic mode.
Exactly, a black box of panic. And the most terrifying part, you check your version control system, you check the logs, and there is absolutely no record of who did it, why they did it, or, what exactly changed.
That is honestly the ultimate DevOps nightmare.
Yeah.
I mean, it is the specific scenario that keeps infrastructure engineers awake at night.
Oh, for sure.
And the crazy thing is, in organizations that are just starting to scale up, it happens with alarming frequency for a very, very preventable reason.
Right, because somebody somewhere ran a deployment command locally on their laptop.
Exactly. No oversight, no tracking. They just pushed it straight to production from their own terminal.
Yeah. So to prevent that nightmare, our core theme today is moving away from those chaotic, scary manual changes and treating your infrastructure as a highly structured pipeline.
Right. It's a fundamental shift, really, in how organizations think about building the environments that their software lives in. We are moving away from that individual hero or rogue agent and replacing that workflow with a completely automated, predictable process.
So let's unpack this a bit. Why is running a command like Terraform apply locally on your machine such a cardinal sin in modern DevOps? Because, I hear developers say all the time, well, the code works on my machine, so I should just be able to push it up.
Yeah, the classic works on my machine defense.
Yeah.
Look, when it is just you working on a side project, a local apply is completely fine.
Right.
But the moment you introduce scale or, collaboration with a team, manual deployments become a massive anti-pattern. First and foremost, you experience a total loss of the audit trail.
Which leads directly to that nightmare scenario we just talked about.
Exactly. In a collaborative environment, if you deploy from your laptop, the rest of the team has absolutely no visibility into the current state of the infrastructure. The changes exist entirely in your local terminal history, right? Not in a shared visible system.
Which means if something breaks, the team is just flying blind. They don't know what changed, so they obviously can't easily roll it back.
Precisely. And beyond just the lack of an audit trail, local deployments completely bypass necessary peer reviews.
Oh, right, because there's no pull request for a local terminal command.
Exactly. If you are typing the apply command and hitting enter, nobody else is looking at that proposed execution plan to say, wait, doing this is going to accidentally tear down our primary database. You're completely removing the safety net.
Wow.
And you also destroy consistency across different environments. Like your laptop might have different local variables or slightly different network permissions
or even a different version of the Terraform binary installed on my laptop.
Exactly. A deployment I run might succeed beautifully, but the exact same code deployed by you on your machine might fail catastrophically.
The way I like to visualize this, and tell me if this makes sense, running things locally is a lot like a blacksmith handcrafting a single car part.
Oh, I like that.
Right. Like it is bespoke, it is artisanal, and while that is fantastic if you are building a custom dining table, it is an absolute disaster if you are trying to scale cloud infrastructure. What we actually need is an automated assembly line.
That is a perfect analogy, because on an actual factory assembly line, every single piece of raw material goes through the exact same rigorous quality checks before it ever becomes a finished product.
Right.
It doesn't matter who loaded the materials at the start of the conveyor belt, the process is identical, it's mathematical, and it's repeatable every single time. That is the exact function a CI/CD pipeline serves for infrastructure as code.
Okay, so we're firing the blacksmith and we're building the assembly line.
Yes.
How do we actually construct this thing? Because the source material details a standard progression, right? Like standard stages that every piece of Terraform code needs to pass through on this conveyor belt.
Yeah, there's a very specific order. The very first stage on our infrastructure assembly line is always Terraform FMT, which stands for format.
Ah, the syntax cleat.
I can definitely feel that way, especially when your pipeline fails over a single trailing space.
Yeah.
But Terraform FMT automatically parses your Terraform configuration files and rewrites them
Yeah.
to adhere to a basic standard formatting convention. It basically ensures spacing is correct and indentation is uniform across every single file.
Which I imagine ends the stylistic holy wars on a team.
Oh, absolutely. It prevents that scenario where two developers are arguing in a code review over spaces versus tabs, or where a file looks fundamentally different just because someone's code editor is configured with weird linting rules.
It just levels the playing field entirely. So once the code is formatted, where does the pipeline move to next?
Next station is Terraform Validate. So now that the code is readable, we need to know if it is actually structurally sound. Validate checks the syntax and the logic of the code without actually trying to reach out and connect to your cloud provider.
Wait, so it isn't talking to AWS or Google Cloud yet. It's just doing an internal check.
Right, exactly. It relies purely on the provider's schemas that are downloaded to the machine. So it is looking for things like missing required arguments, undeclared variables, or, structural errors.
Like what?
Well, for example, if you try to assign a string to a variable that expects a list of numbers, Validate will catch it and throw an error.
Got it. So formatting handles the style, and validation catches the logic errors. And neither of those stages has actually touched our live cloud infrastructure yet.
Correct. They're entirely safe, local checks that the pipeline runs automatically. If the code fails either of these initial stages, the assembly line stops immediately.
The red light goes on.
Yep. The pipeline is marked as failed. The developer gets some... If it passes, we move to the critical stage, which is Terraform Plan.
The preview of the impact.
Exactly. Terraform Plan is where the system finally looks at your code, looks at the current state of your actual live infrastructure, and calculates the delta.
So it figures out the difference between what exists and what you want.
Right. It figures out exactly what changes need to be made to make reality match your written configuration. And it output a comprehensive line-by-line list. Like, it will add these 3 servers, modify this one firewall rule, and destroy this old database instance.
Now, according to the standard pipeline architecture we're reviewing here, the very next step after the Terraform plan generates that preview is a manual approval gate, meaning a human being actually has to step in, look at the plan, and click approve.
Yes, that's the standard practice.
Well, I have to push back on this design a bit. I mean, if the entire point of building this assembly line is strict automation, removing human error and firing the blacksmith, why are we injecting a human choke point right in the middle of our automated pipeline? Doesn't that defeat the purpose?
That is a totally fair question. And honestly, it is a friction point that trips up a lot of teams when they are first transitioning to CI/CD.
It just feels counterintuitive.
It does. But the automation in an infrastructure pipeline doesn't exist to remove human intelligence entirely. It exists to guarantee that the checks and balances happen every single time without fail. The pipeline automates the generation of the plan perfectly, but we have to consider the blast radius.
The blast radius. So
Yeah.
the difference between an infrastructure change versus a normal software change.
Exactly. If a software bug makes it through a pipeline and into production, maybe a checkout button on a website stops working, or, a feature fails to load. It is bad, obviously, but it is usually isolated.
Right.
But if an infrastructure bug makes it to production, you might accidentally delete the entire virtual private cloud networking layer for your entire company. The blast radius can be total catastrophic failure.
Deleting the production network is what they call a resume generating event.
Exactly. A very fast way to get fired. So because the stakes are incredibly high, a human, usually a senior engineer or a designated peer reviewer, must evaluate the output of that automated plan.
Okay, I see.
They need to analyze that list of additions, modifications, and crucially, destructions. They have to confirm that the pipeline's intended actions actually match the business intent. And only after that human verification does the reviewer pull the final lever to authorize the Terraform apply stage.
And the Terraform apply, which is the stage that actually reaches out to the cloud APIs and provisions the resources, that only happens upon merging the code to the main branch, right?
Yeah. Yes. Applying only on the main branch ensures that your main branch is always a truthful, perfect representation of what is actually running in the production environment.
Okay, so the flow is format, validate, plan, human review, and apply.
That's the assembly line.
But looking at this mechanism, if I'm the reviewer at that manual gate, I spot a massive vulnerability in this workflow.
Oh, really? Let's hear it.
Well, okay. The automated system runs Terraform plan. It calculates it needs to build 3 specific servers. I read the plan at the approval gate, everything looks perfectly correct, and I hit approve.
Okay.
The system then moves to the Terraform apply stage to build them. But what if, I don't know, in the 10 minutes between the plan finishing and me hitting approve, the cloud environment changes?
Ah, I see where you're going.
Like, what if someone manually tweaks the security group in the AWS console, or an auto-scaling group scales up? When the apply stage runs, doesn't it just recalculate based on the new reality and potentially build something completely different than the exact plan I just approved?
Your paranoia is entirely justified. That is a very real threat. In a busy, dynamic cloud environment, the state of the infrastructure changes minute by minute.
Right.
If the pipeline just ran a fresh apply command, it would recalculate the delta. And it absolutely could execute changes that the human reviewer never actually saw.
Which defeats the point of the review.
Exactly. And that critical vulnerability is exactly why the 003 exam material heavily emphasizes something called the plan artifact pattern.
Okay, a plan artifact. Now, in normal CI/CD terminology, an artifact is usually just like a compiled binary or a zip file that gets passed between jobs. How does Terraform use an artifact to solve this drift problem?
So instead of just printing the proposed changes to the console text log for the human to read, the pipeline is instructed to take the output of the Terraform plan stage and export it as a discrete binary file. That is the plan artifact.
Oh, I see.
This file contains the exact state of the world at the very moment the plan was run, along with the precise cryptographic calculations of what needs to change.
It is essentially freezing the blueprint in Carbonite.
Yes, perfect way to put it. Then, when the pipeline moves to the final Terraform apply stage, we don't just tell Terraform to apply our code configuration. We instruct the apply command to consume that specific saved binary artifact.
So you're forcing it to use the old plan.
Right. We pass a flag to the command that essentially says, do not recalculate the delta, do not look at the current state of the cloud, execute this exact saved blueprint, bit for bit, and nothing else.
But wait, if the cloud environment did shift underneath us during those 10 minutes, say someone did manually delete a subnet, what happens when the apply tries to run the artifact?
The apply will simply fail.
Really, it just stops.
Yeah. Terraform will detect that the real-world infrastructure no longer matches the assumptions that were baked into that binary artifact. It aborts the operation safely rather than try to guess how to reconcile the differences and, making a disastrous mistake.
Wow.
Yeah. The plan artifact pattern completely eliminates the window for configuration drift. It guarantees absolute consistency between what was approved and what is actually executed.
That is brilliant. It is building a safety net out of pure logic.
Yeah.
Okay, so we have the theory of the assembly line down. We understand the standardized stages. We understand the blast radius justifying the manual gate and the plan artifact preventing drift.
Right.
Transitioning from theory into actual implementation, how does this conceptual assembly line live inside a specific tool like GitLab CI/CD?
So in GitLab, your entire pipeline is defined within a single YAML file, typically called .gitlab-c.el.
Okay.
This file lives right in the root directory of your code repository alongside your actual Terraform.tf files. It's basically the definition of infrastructure as code applied to the pipeline itself.
So it's pipeline as code.
Exactly. Inside that file, you write the logic for the jobs. You write the format job, the validate job, the plan job, and the apply job.
So you are writing code to tell a runner how to test and deploy your other code. But that actually brings up a massive logistical hurdle that teams run into immediately, right? The Terraform state file.
Ah, yes, the state file.
For anyone learning Terraform, the state file is essentially the program's memory. It is a highly sensitive JSON file that maps the resources written in your code to the actual physical resource IDs in the real world.
Right, it's the source of truth for Terraform.
Exactly. If you lose the state file or if it gets corrupted, Terraform suffers amnesia. It completely forgets what it has built.
Yeah, and in a local blacksmith-style deployment, that state file just sits on your laptop's hard drive.
Right.
But in a CI/CD pipeline, the environment is ephemeral. The pipeline spins up a brand new empty runner, executes the jobs, and then completely destroys itself.
So the state file absolutely cannot live on the runner because it would just be deleted the second the job finishes.
Exactly.
And you can't just commit it to your Git repository because it often contains plain text secrets and passwords, right?
Yes, please never commit your state file to Git. But honestly, even more dangerous than where it lives is the problem of concurrency.
Currency.
Yeah. Imagine a scenario where two different developers merge code at the exact same time. Two separate CI runners spin up. They both read the state file, they both try to provision resources, and they both try to write their new updates back to the state file simultaneously.
Oh, wow. The state file gets torn in half. It just gets completely corrupted.
Yes, which is why platforms like GitLab provide a managed Terraform backend. It securely stores your state file within GitLab's own database infrastructure.
Oh, okay.
And when your pipeline spins up, it reaches out to that remote backend and requests an exclusive lock on the state file.
It essentially puts a padlock on the memory bank.
Exactly. While runner A has the lock, if runner B spins up and tries to run and apply, the backend denies access.
So runner B has to wait its turn.
Right. Runner B has to wait in line. Runner A reads the memory, provisions the cloud resources, updates the state file with a new reality, and then securely unlocks it.
It guarantees that only one automated process can alter the infrastructure at any given millisecond. That is super elegant.
It is.
Okay, so that handles the memory, but what about the keys to the kingdom? Because if our automated pipeline needs to go out and actually build servers in AWS or Google Cloud, it requires administrative credentials to authenticate with those cloud providers.
Yeah, authentication is the other huge hurdle.
And the absolute golden rule of DevOps is that you can never, ever hard-code AWS access keys into your code repository.
Never. Because if you hard-code your credentials, anyone with read access to your repository, which, could be hundreds of people in a large organization, or the entire internet if it accidentally goes public, they could just steal those keys.
Right.
They could spin up $1 million worth of crypto mining servers on your company's dime before you even realize what happened.
It happens all the time. But if the pipeline needs the keys to build the infrastructure, but we are strictly forbidden from putting the keys in the code repository, how do these CI/CD tools actually solve the authentication problem?
Well, the legacy solution, and honestly one you will still see a lot, is using CI/CD masked variables.
Okay, how does that work?
You log into the secure web settings of your GitLab repository, and you manually paste your permanent cloud credentials into the interface, and you mark them as masked.
Which just means that if the pipeline ever tries to print the variable to the console log, the system intercepts it and prints a bunch of asterisks instead.
Right. The pipeline pulls those variables at runtime to authenticate. But the industry has recognized a pretty severe flaw in this design.
It is.
Masking the variables prevents them from showing up in logs, sure, but you are still taking long-lived, permanent administrative passwords and storing them in a third-party system. If that CI/CD platform ever gets breached, your permanent keys are totally exposed.
So masking the variable is really just hiding a permanent physical house key under the mat.
Exactly.
Like, it is out of sight, but the key still opens the door forever if someone finds it.
Perfect analogy. Which leads us to the modern solution, and the one that the HashiCorp exam heavily focuses on, which is OIDC, or OpenID Connect.
OIDC. Okay, so how does OIDC fundamentally change the architecture here?
It fundamentally changes the architecture of authentication by using dynamic credentials instead of permanent passwords.
Okay, dynamic credentials. Explain the mechanics of that cryptographic handshake. Like, how does OIDC provide access without storing a permanent key anywhere?
So OIDC relies on identity federation. Instead of giving GitLab an AWS password, you configure a trust policy in AWS. You basically tell AWS, I want you to explicitly trust this specific GitLab repository.
Okay, I follow.
Then, when the pipeline runs, GitLab generates a temporary cryptographic token. It's called a JSON web token that proves the identity of the pipeline.
So the pipeline takes that token and essentially knocks on the AWS door.
Right. AWS inspects the token. It validates the cryptographic signature against the trust policy and says, okay, I recognize you. AWS then uses its security token service to generate a brand new set of short-lived temporary credentials and hands them back to the pipeline.
And the crucial part here is that those temporary credentials have an expiration timer hard-coded into them, right?
Yes. They are valid for the exact duration of that single pipeline run, maybe an hour. As soon as the pipeline finishes, those credentials just evaporate into thin air.
Wow.
Even if an attacker somehow intercepted them, by the time they try to actually use them, the credentials would be worthless.
It is the difference between giving someone a permanent metal key to your building versus giving them a temporary hotel key card that automatically deactivates at checkout.
Exactly. No permanent secrets are ever stored, and the attack surface is reduced to almost zero.
That is so much more secure.
It is. And that architectural shift from static variables to dynamic OIDC authentication is exactly the kind of conceptual understanding the Terraform Associate 003 exam is testing.
Well, speaking of the exam, for our listeners who are specifically preparing for that 003 certification, how do these concepts translate to the actual test? I mean, HashiCorp isn't testing whether you can memorize the exact YAML spacing for a GitHub Actions workflow, right?
No, not at all. They know that in the real world, you are going to look up the specific syntax in the documentation.
Thank goodness.
Right. The exam evaluates your ability to make sound architectural and design decisions when integrating Terraform into an automation pipeline. They basically want to know if you understand the why behind the tools.
Okay, let's test that logic then. Let's walk through 3 common scenarios that mirror the type of problem solving the exam requires.
Let's do it.
Okay, scenario 1. Imagine a scenario where a development team is experiencing constant outages. Their production infrastructure keeps changing unpredictably, resources are being orphaned left and right, and the team lead cannot figure out who is making the changes. The mandate is to enforce visibility and consistency.
So in this case, the exam wants you to identify the core anti-pattern causing the chaos.
Right. If the team lacks visibility and history, it means engineers are still doing local, manual applies from their own machines.
Exactly.
So to solve that, the architecture has to move to a centralized CI/CD pipeline. All kind must run through the standard stages format, validate, plan, apply, so every change is captured in a central auditable system.
Spot on. It's about recognizing that a standardized pipeline is the cure for the local execution anti-pattern. Okay, let's do scenario 2.
Get me?
A highly regulated financial company has implemented their pipeline. They have the manual approval gate in place.
Yeah.
But an external auditing firm comes in and demands absolute mathematical proof that the infrastructure changes executed against production are the exact unaltered changes that were approved by the senior engineer.
Oh, okay. So if the auditors want an absolute guarantee, running the plan and apply commands sequentially just isn't enough because, like we discussed, the state of the cloud can drift in the gap between the commands. So to prove consistency, the pipeline has to generate the plan and freeze it by writing it to disk as a discrete artifact. The pipeline architecture must be designed so the apply stage explicitly consumes that specific binary file.
Exactly. That tests your understanding of the mechanism that prevents configuration drift.
Awesome. Okay, final scenario. The Security Operations Center has issued a strict mandate. Your Terraform pipeline needs to provision highly sensitive database servers, but you are strictly forbidden from storing any permanent administrative credentials within the CI/CD platform's secret manager, citing the risk of a platform supply chain attack.
So hard-coded keys are completely out.
Right. But masked variables in the CI/CD settings are also out, because even if they are hidden behind asterisks, they are still permanent credentials sitting in the third-party system.
Correct. So what's the solution?
To grant access without storing permanent keys, you have to establish OpenID Connect. The pipeline runner authenticates via identity federation, receives a temporary lease from the cloud provider, does its job, and then the credentials expire immediately.
Yes. Navigating those trade-offs is exactly what separates a junior operator from someone who truly understands infrastructure automation at scale.
This has been super illuminating, just distilling all of these sources down for everyone listening. When you are dealing with infrastructure as code, the code itself is really only half the battle. To operate at scale, you have to treat your infrastructure as a pipeline.
Absolutely.
Moving away from those artisanal manual applies and building an automated assembly line is the only path forward. Standardize validation stages, catch errors early, plan artifacts, freeze your blueprints to prevent drift, and handling authentication with dynamic trusts like OIDC ensures your systems remain actually secure.
Yeah, and whether you are deep in preparation for the HashiCorp exam or you are simply trying to stabilize your company's cloud environment, mastering these pipeline design patterns is what transitions a reactive, chaotic team into a truly mature DevOps culture.
Couldn't agree more. Before we wrap up today, I want to leave you, the listener, with a final thought to mull over. We have spent this entire deep dive discussing cloud infrastructure and automated servers. But think about your own day-to-day workflows, even entirely outside of writing code.
Oh, that's interesting.
Where in your life are you still relying on manual applies? Where are you executing major decisions or projects on the fly, doing things by hand with absolutely no safety net, where you could genuinely benefit from building a personal assembly line? What would it actually look like to build a personal plan artifact, to meticulously preview the results and the blast radius of your actions, and freeze that blueprint before you finally commit to the change? Something to explore on your own. We will see you on the next deep dive.